So my name's Peter Hopton. I'm the dissemination lead for EuroExa, and we're tasked with co-designing development of technologies for Exascale under the project name EuroExa. I'm the founder of Iceotope, and I also chair the Committee for Data Centers at the Chartered Institute in the UK, and I'm the deputy chair of the Future Computing Systems Group at the Chartered Institute. So here in the EU, we have a route to Exa-Scale, not dissimilar to the United States or other countries that are participating, such as China, Russia, Japan. And we're looking around 2021 to 2024 for the first Exa-Scale machine being turned on. We don't know exactly when that procurement's going to take place yet, which is why there's such a wide range. And as you'll learn in a little bit, that wide range means that we could end up with dramatically different costs or power consumptions of the system. But in terms of our project, we're thinking about 2021 and enabling an Exa-Scale machine for 2021. So within the EU, we started off with the first H2020 FET HPC projects in 2015. And each of these were focused at a particular subject area. There wasn't really a co-design consideration. And then a number of those came together in competitive exercises in 2016, starting in 2017. They're called co-design projects. It's expected that we'll have our first Exa-Scale demonstrators running in 2019, and they'll be able to then prove scalability all the way to Exa-Scale. I'm pretty sure everyone in the room knows what Exa-Scale is. However, I'll go through it anyway. It's a billion floating point operations per second, or equivalent. And what we're looking at here is a substantial improvement in energy efficiency to be able to achieve that. Now, depending on when one's procured, it's expected it's going to be between 100 million euros and 500 million euros per system, and anywhere from 20 to 60 megawatts of power. Now, that's a big data center, and that's a big computer. 60 megawatts is about the biggest data center on the planet. So if we make a computer that big, it's the likes of some of the biggest data centers in the world in terms of power consumption. Now, the EU is expected to procure 2 systems, and they're saying that one will be procured from an EU-only consortia. It's expected the other one's likely to come from the United States. And one of the things within the EU is we don't necessarily have an ecosystem to deliver. We don't have the large vendors like Cray and Intel. So one of the things we've got to do is build an ecosystem to be able to deliver that supercomputer that's going to be provided by an EU consortia. And of course, this has been an EU objective for a while, to try and build a domestic supercomputer industry. In the run-up, there's also expected to be pre-Exa-Scale machines, so machines of around 100 petaflops or so. Well, there's a number of big challenges for Exa-Scale, and I'm sure a lot of people in the room are familiar with a number of these. Programming models, of course, when you start scaling over hundreds of thousands of nodes. Resilience and reliability, once you've scaled out that far. Will you ever actually finish your job? Or you end up having to constantly reset it and go back to your last checkpoint and then try again? Will the job ever finish if you've got nodes falling over? Because when you've got 500,000 nodes running a parallel job, well, statistically, one's going to fall over every 10 minutes. When you look at organizations that have built data centers that are of the 60 megawatt or so size, they have 20 or so people going around the data center in small mobility carts with a number of spare parts, fixing one fault every 15 minutes each. Imagine that in terms of an Exa-Scale supercomputer, having to constantly maintain those faults and fix those issues. And how's that going to disrupt the running of the tasks? Supply chain, a big issue here in Europe. And, well, scalability, considering those elements. One of the biggest issues is around the size of the machine. In that if the machine gets too big, it starts to lose its efficiency because your latency from one side of the machine to the other becomes longer, the distance becomes longer, the amount of energy that has to go in to transmit and receive the data becomes higher. So a big thing around this is you can't make a 60 megawatt data center of the scales of the hyperscalers where they deploy at 10 kilowatts a cabinet. You need to make it a lot more compact than that. Otherwise, you're looking at potentially a mile from one side of the data center, one side of the supercomputer to the other side of the supercomputer. You've got to try and bring that in and make it of the order of 50 meters or so. And a big part of that, well, it's energy effectiveness. Because if that data center is too big, and that supercomputer in that data center is too big, it's taking up too much area, and that distance is too high, simply this thing is going to consume too much energy. And if it consumes too much energy, it won't be running, because we won't be able to afford to run it. So energy is king in this issue. Many of you would have heard of Moore's law, but one that hasn't been mentioned today is Kuhme's law, and another one, Shannon's law. Kuhme's law is tied to Moore's law, and it talks about how computers get more energy efficient at doing computations every 18 months. Shannon's law. Anybody in the room know what Shannon-Hartley theorem is, or Shannon's law? No? No hands? It's a fundamental limit in physics for the transmission of a bit of data over a piece of distance in copper. And it's a limit of physics. It's the bit that can't be improved because it's a law of physics. And you can see it in this graph from the University of Manchester. The blue line is 2008 at 45 nanometers. And you can see on the left side the energy used to process the data. And the red line is a more recent 11 nanometer 2018 device. You can see the device has become much more energy efficient, 10x more energy efficient in doing the processing of the data. But as you follow the lines along, you'll find that they converge. There's an area where there's been no improvement whatsoever in the last 10 years or so. And that area is around the transmission of data on chip, off chip, to RAM. It's not changed. And what we're seeing is, as a result of this, having to move components closer together and reduce that distance. Because actually, the amount of energy being used to transmit the data off the chip is similar to the amount of energy being used to process the data on the chip. And that is limited by a law of physics. So it doesn't matter how much more efficient we get at processing the data, if we're going to have to spend that energy to transmit the data off, we're not going to be able to continue to produce order of magnitude improvements in energy efficiency overall. So what we're going to do is physically move things closer together to get over that limit. And that brings about a density problem, a problem relating to how you're going to deliver power and remove heat. And that's becoming a big part of this. And Seymour Cray actually said it back in the 1980s. The main issues making a supercomputer at the time were the cooling and the thickness of the wiring mat. So EuroExa, what is EuroExa? Well, there was an EU competitive exercise, and it selected a number of partners. 3 of the previous 2014, 2015 projects came together. Some other partners came in. An amount of IP was committed by ARM and Synopsys to the project. And then EU funding and monitoring to create EuroExa. And you can see the EU describe it like this. Groundbreaking design for mind-blowing results. 4 times more performance and 4 times more energy efficiency. Well, that's what we're trying to do. So who's been selected in this competitive exercise? Well, first of all, you'll notice Barcelona Supercomputing Center up there. A number of commercial partners, academic partners, government partners, and, well, some very high-end supporters of the project. So the next 3 years, what we're going to try and do is deploy 3 test beds. The first test bed will be installed in 2018, providing 50 nodes of a new technology for software deployment and development. And these new nodes have been produced as part of the previous projects and will be coming into our project to set up the test bed. And we'll then be looking at a second test bed, which will be providing 500 nodes to test the scaling of the nodes. And then a third test bed that will be installed in 2020 to test new node technologies that will be coming into the project. So that second test bed, 500 nodes, we're expecting around a petaflop or 2 of performance out of that, in a cabinet or less. In terms of the architecture of the system, ARM processors and FPGA accelerators, with FPGA data flow brought by Maxella Technologies. A UniMem architecture with a partitioned global address space. Distributed storage on BGFS, and as part of the work that Fraunhofer has done, also distributes the control, command and control of that storage as well across the system. So every node will have storage. Every node will be identical, and that storage will be distributed. ZeroPoint have brought memory compression technologies to help us in terms of that transmission of data. If we compress the memory, we use less of it, and we transmit less data. And there's also some very interesting interconnect technology that's being developed by the University of Manchester. In terms of applications, they're expected to be run and tested: climate, weather, physics, energy, life sciences, and bioinformatics, being brought by a number of the partners. Yeah, I'm sure a lot of you guys will know European Centre for Medium Range Weather Forecasting and the Hartree Centre, or STFC, University of Manchester. INAF is the National Institute of Astrophysics in Italy. INFIN is the National Institute of Nuclear Physics in Italy. Fraunhofer, Erasmus, Synalexis, Barcelona Supercomputing Center, and IMEC. So when it comes to the nodes, I have to apologize for some of the censorship of this slide. There's some technology from Forth. And they're 12 by 13 centimeter nodes with 4 processors and 4 accelerators on them. So imagine, your normal motherboard is the size of a pizza box. It's normally, 15 inches or so diameter and depth. That's been shrunk into something that's a 12 by 13 centimeter unit with 4 processors and 4 accelerators on it, an SSD, a whole load of RAM on the underside layered up. And it forms a daughter board, which I consider a standard kind of beer mat daughter board. And it's got 160 gigabits a second of I/O coming off of it. And we take these nicely compressed nodes and we pack them in really, really tight, like this. So this is a unit that's got 16 of these quad processor servers inside of it in a single 1U box. Now, these 1U boxes are short depth. The idea is that within a single cabinet footprint that would conventionally be used, we fit 2 cabinets back to back, or cabinets against a wall, and that would enable twice as much stuff per U within that conventional footprint. That's 3.2 kilowatts of electronics in that single U box, and that's after we've gained the energy efficiency from doing all that compactness. The technology used to cool that 3.2 kilowatts in that 1U box is a total liquid cooling technology that immerses the electronics within liquid fluoroplastics that circulate around the box. There's 48 volt DC power coming in the back. that's delivered directly to the door-to-board point-to-load converters. This saves around 10 to 20% off the total energy bill of the system by taking this step. Because normally within a system, you end up delivering the power AC to the UPS, converting it to DC, converting it back to AC, coming out, converting it to 12-volt DC, transmitting it into the circuit board, and then converting it down again to the actual points of load. By simply taking 48-volt DC, we do one conversion step. The batteries are connected to that DC bus, and it goes straight to the daughter cards, and then gets converted to the point of load. 20% of the power saved. And part of this is hot water cooling. So we're looking at 45 degrees Celsius inlet coolant temperatures as our target. And the idea here is that no chiller plant will be used in the running of these systems, maximizing the energy efficiency. Here's a little bit more about that box. If you look at the rear of the box, you'll notice some heat exchangers and some pipes. That's the cooling system, taking up that whole rear portion of the box. And then at the front are the I/O connectors. Notice they come out sideways, like a hammerhead. The reason they come out sideways is it dodges one cable bend. Because normally your cables will come out front, and then you'd have to bend them 90 degrees. Bringing the cables out sideways means we dodge that cable bend, and that makes a big difference in terms of the amount of energy consumed from point A to point B within the system, and reduces the depth of the unit. The magic number we're aiming for is 762 millimeters from the very front of the box to the very back of the bus bar. And that's a magic number. Taking all of the gubbins out, this is the mezzanine that's left, and on there, a switch on the underside. And that switch connects all of those daughter cards together and then uplinks them to the rest of the system. Just a little GIF I like to show. It's not technically 100% accurate, but it's entertaining. So we take these 762 millimeter deep cabinets and we back them against a wall of an ISO shipping container. That way we create a single aisle up the middle with the row of cabinets up the left and a row of cabinets up the right. And we fit 2 megawatts of equipment into a single shipping container. This makes the distance from one side of the computer to the other side of the computer a lot more interesting. Because previously, we deploy them in a big square on a single level. And when you deploy them in a big square on a single level, the distance from one side to the other side is a long way. But if we put them in shipping containers, we can stack them three-dimensionally into a big cube instead. And that substantially reduces the distance from one side to the other, which then makes energy efficiencies and allows us to make the whole system more effective. Hence, co-design, thinking about all these things as they stack up. And, well, we won't be the first people to make a data center out of shipping containers. Here's one in Lagos, Nigeria, that's been designed. Each of those huts on the rear side is a stack up of shipping containers. And I would estimate that one of those could be our Exa-Scale computer. These guys here. You can see a stack up of shipping containers just there. And then coolers and power delivery. In terms of the stack up of the computer itself, this gives you an idea of the stack up of the electronics and resulting performance. So it starts at the processor units, 600 gigaflops each, 2.4 teraflops per node, 38 teraflops per blade, 230 teraflops per subrack, a petaflop per net group, 2.7 petaflops per rack, and then up to 400 petaflops for a whole system within a budget of about 15 megawatts. Sorry, 30 megawatts. Get my numbers right. So the system hopes to demonstrate that we can have a peak performance, a scale to a peak performance of 400 petaflops with an estimated system power consumption of 30 megawatts. That's what we're going to show as part of this project. That's what we're going to prove. And that would enable a compute-centric quarter exaflop for 15 megawatts by 2019, potentially enabling a 60 megawatt, 30 shipping container Exa-Scale supercomputer in 2021. That's the end of my presentation. Please connect to me on LinkedIn. If you type in thecoolingguy.me, that will bring you to my LinkedIn blog. Please come and connect, ask questions, and I'm quite happy to take questions now, if there's any in the room.